go ahead and start here. Our question today is, big one is, how do mechanical waves propagate? Okay, you can see that. How do they propagate? There's two ways that we look at waves. In other words, we look at them as either a packet or as a waveform. And when we say packet, we're talking about a pulse. We pop something and like you thump Jello, and that's one pulse. And what happens? You drop a stone in a pond, what happens? Okay, that's considered a pulse. We have a single disturbance in the medium. Now, the medium itself is what the waves are traveling through, okay? And it says that right there. All mechanical waves require a medium. It should be median. It's a medium to travel through. And the medium is the substance that is propagating the waves. Okay? That would be like your water or your Jello or air or whatever it is. Okay? String, a slinky, a spring. We're going to look at all of those today. A wave is a series of pulses. It's continuous pulses, if you want to think about it that way. Okay? Waves are what carry energy through a medium. All right, so I need you to make sure you read this right here. It says waves transport energy, not matter. The matter is just what they go through. The wave is the actual mechanism by which the energy moves, okay? So let's talk about the two different types of waves. We have what we call a transverse wave, okay? What is a transverse wave? All right, so if we look at a transverse wave, and I've got this guy right here. Okay? If we look at a transverse wave, and we're looking at a transverse wave here, this is a transverse wave. As we're doing it, if you put this on it, you can see it's going up and down along the length, right? It's not, the medium itself is moving. The string is the medium, or the spring is the medium itself. It's moving, and it's going up and it's going down. There's a difference between a transverse wave and what we call a longitudinal wave. So you saw what the transverse wave was. I can't really make a longitudinal wave with this guy, but I can with Slinky. Longitudinal wave is where it travels along the body of the wave longitudinally. So if I were to do this, if I were to see how it's moving this way, the pulse, you can follow it this way. So this is longitudinal versus this is transverse. You see the big difference between the two now? All right, so it's almost like the pulses, they're both getting pulses. It's just this one is traveling all the way straight through versus this one where it's moving it. Pretty easy to see. You're still getting, see what I mean about, this would be one pulse. Continuous pulses create a wave. Same with this. One pulse, you can see it, versus you get a wave. All right? So that's what the slinkies and the springies are for today, to look at this, physically look at what we've got going on. So in a transverse wave, the vibrations move perpendicular to the direction of the wave's motion. Think about why it's perpendicular. Think about which way the slinky was going. The wave was moving this way from beginning to end, but the actual spring was moving up and down. okay? A good example of this would be a wave, when you do the wave at a sporting stadium. Like if you're at a football game and they have you do the wave, what happens? Everybody stands up and down, but the wave goes around. So ocean waves are the same way. Think about it. What is an ocean wave doing? The water is literally swelling and going down, but at the same time it's traveling towards the shore, isn't it? Or away from the shore. All right, so waves can be described in terms of position from equilibrium. You've seen this before. Crest. Crest is going to be the high point, the highest point, okay? It's the highest point above equilibrium. Trough is going to be what then? Yep, lowest point. Oh my God, that's funny. Sorry. Okay, what is the wavelength? Well, yeah. One complete wave has one crest and one trough. So there's a crest, here's the trough, right? So the wavelength is literally going to be from here to here. Okay, so wavelength is there. So that is going to be length of one complete wave. Okay, and amplitude. Amplitude is just that distance to the crest or that distance to the trough from equilibrium, okay? It's their max displacement from equilibrium. So this is my amplitude. So it's from equilibrium. So the distance from crest to trough is actually twice the amplitude. Okay? So that is transverse waves. Got any questions so far? Nah. Now, look at longitudinal waves. We've seen those. So in longitudinal waves, the vibrations move which way compared to the direction of the wave's motion? Parallel. Yes. To the direction of the wave's motion. So, and it gives you an example when the spring is stretched or compressed, it vibrates parallel to the length of the spring. So you've got right here what we call a compression. And right here, after the compression, in other words, it bunches up, and then what does it do? Stretches out, and that is called a rarefaction. So the rarefaction is going to be the less dense portion of the wavelength. And you can guess that the compression is going to be the more dense proportion. Right? And not all waves are transverse or longitudinal. They're not one or the other. Some are both. Light is considered to be a transverse and longitudinal type of wave. So is energy, so is like waves in the ocean. because they will still push you as they are going up and down. So they are experiencing both. All right. So let's talk about phase. Are 2 points in a wave in phase? Phase is the location of a point within the wave, okay? I want you to think about that. They are in phase. In other words, if they are in phase, they are moving in the same place at the same speed, okay? So what does that mean? It means that which pair of points are below are in phase with each other if they have the same displacement from equilibrium at the same velocity, okay? So which parts are in phase? Yep. So A and E are, what else? Yep, B and F. C and D are not, nor are they in phase with anything else, okay? They've got to be in the same basic place at the same basic speed, okay? Now, what could we say about A and C? Maybe I should preface this by saying, when you think of a wavelength, remember we studied sine? We studied sine as a circle that's been taken apart. Same with cosine, right? So we can look at this from A to B to C to D to E are all, that's one part of the circle, isn't it? So if we were to go right here, we would start at A, and C is exactly opposite, isn't it? B and D are not. B and D are somewhere in between, so it's most of the way. So B would be like here, and D would be like here. And then E would be back up here again, wouldn't it? So we can see that A and E are. And we can see that B and F would be because B, and then this would be F again, wouldn't it? All right, so if they're in phase with each other, when you drew it in a circle, they would both end up at the 360 mark, okay? So in phase, they are in 360 degrees from each other. In other words, if we put them on 360 degrees means they're in the same spot in the circle every time, aren't they? What we consider out of phase, it really depends on what degree they are from each other. So look at A and C. How many degrees off are they from each other?
A and C?
Mm-hmm. So they'd be considered 180 degrees out of phase. What about B and C? We'll have to estimate a little bit, won't we? But how many degrees do we think there is between these two? How many degrees? Let's call it theta. So B and C would be considered theta degrees out of phase. We could estimate and say it's maybe like 50, 60 degrees. If it gave us an exact, we could say what it was, right? But do you understand in phase versus out of phase? For them to be in phase, they would be in the same point in the circle. If we were to take the wave and turn it into a circle, out of phase means they would not be in the same point. All right, look what it says. What did it say the frequency was defined as? Here we go. Trying to find where we put it. Look at some things. Period. Things we need to know. Period is the time to complete one cycle, right? The formula for period for this, if we want to think about it, would be the length of the wave divided by the speed of the wave. Okay? Frequency is cycles per second, and please remember that frequency is just 1 over the period. Now, I want you to think about what the length of a wave would be. Remember, the length of the wave, you can take one full set of the wave and it becomes a circle, doesn't it? Well, how far is it all the way around a circle? Circumference, isn't it? Length, not degrees. And circumference is, so this becomes 2 pi r over the velocity, the speed of a wave. So it's 2 pi r over v. Well, frequency is just 1 over the period, so it actually becomes the velocity divided by 2 pi r, doesn't it? Period is seconds. This would be units are in seconds. Frequency is units is 1 over seconds, which is the same as hertz. Okay? Hz is for hertz. Now, wavelength. Remember what we said the wavelength was? We said wavelength would be between, be 1 full cycle, right? So if we did this, hold on, let me think. Do this, up and back down, and back up again. So it would be from here to what, to here again? That would be 1 wavelength? Okay. So 1 wavelength would be consecutive points that are in phase. Wouldn't these two be in phase then? So this would be 360 degrees in phase, right? And so wavelength would be the distance between theirs. Okay. And since wavelength is a distance, by the way, it's this guy right here. Lambda is your wavelength. And it is measured, its units, since it's a distance, is just going to be meters, isn't it? Okay. Wave speed. Think about it. Wave speed would be your velocity. Okay. That is going to be 1 wavelength in 1 period, right? That would be your speed, meters per, or distance over time. So that is going to be wavelength over period, will give you your velocity. Well, 1 over t, so think about it as this. This times 1 over t. Well, 1 over t is just frequency, isn't it? So your wave speed is the frequency times the wavelength. This guy right here is the most important formula you're going to find that you'll use out of this. And velocity's units are meters per second, aren't they? Now, I want you to read what it says right here. What does wave speed vary based upon? Yeah. Think about why that is. Medium it's traveling through. If something is got, I want you to think about this. We're transferring energy, aren't we? Think back to thermodynamics. When we talked about transferring energy, what we were talking about is things vibrating, right? Well, how easily something vibrates, how well it vibrates is going to transfer that energy from one to another. So you've got all these things vibrating and it's taking one to another, and that's traveling, the energy traveling along. That's got something to do with this now, doesn't it? Okay, so 2 things affect that. How well something transfers energy. How elastic it is. The easier it does, the more elastic it is, the faster the wave's going to be, right? Because it's going to want to spring back. The more elastic it is, it's going to want to spring back faster, so it's going to send it faster. And how dense it is. Density is going to slow your wave down. Think about it. If it's looser, then there's a lot more room for things to move around, isn't it? When you start packing all of those atoms and stuff in that same space, it doesn't leave them as much space to move, to vibrate, does it? So that's what we need to look at. So two factors determine the wave. So you're going to have elasticity, your wave speed, elasticity and density, okay? And the big thing we need to know is more elastic means a faster wave and denser means a slower wave. All right. And then what's the next second thing it says? Wave speed remains constant unless a wave travels to another medium. So if I went from a slinky to a string, it's going to be different, isn't it? The slinky may make big waves because it's very elastic and the string's not very elastic. So you're going to go from big waves to smaller waves. It'll still transfer, but it's going to transfer at a different speed because the characteristics of the material changed. It really makes sense if you think about it. All right, so let's put some of this to work. We have the end of a string. It vibrates 3 times each second, producing a wave 8 meters long. So what I want you to think about is it says, what's the period of the new wave? It says if the string instead vibrates 5 times per second. So if we have something vibrating so many times each second, per second, is that a period? Is that a frequency? So it's given us an initial frequency. So this is our initial frequency. What is the waves are 8 meters long? What is that giving me? Wavelength. So it says instead it vibrates 5 times per second. What is the new period? So what is the relationship in part A? What is the relationship between frequency and period? Period is 1 over the frequency, isn't it? So if we want to know the new period, we just need to plug in the new frequency. So the new frequency is just going to be 1 over what? Okay, which makes it 0.2 seconds is the new period. So every 0.2 of a second, it completes a cycle. Then it says, what's the new wavelength? Well, that's where this comes into play. Did we change the medium? We didn't change the medium, did we? No. So the wave speed remains constant. That's V. So we know V initial has to equal V final because it did not change. We didn't change what we were putting it through. So the initial velocity is what? F times lambda? Frequency times the wavelength, right? So the initial frequency times the initial wavelength has to equal the final frequency times the final wavelength, doesn't it? So let's fill those in. What was the initial frequency? 3. Okay. What was the initial wavelength?
8.
Final frequency was 5. And we don't know the final wavelength. That's what we're looking for. So now we can just solve it. What'd you get?
4.8.
Yeah. Easy enough, right? All right, so let's look at another one. It says, at a given instant, a wave crest is under one edge of a dock and a trough is under the other edge. There are 3 crests under the 4-meter wide dock. If 25 crests pass by the first edge in a minute, then what's the speed of the waves? So I would suggest we draw a picture. We have the dock here, don't we? So it says we have 3 crests underneath the dock. All right, so crest, crest, crest. Okay, and trough is under the other edge of the dock. Okay, so hang on. I gotta make my dock a little bit longer here because there's my trough, right? So this goes with this, and this is the crest right here on the other end. And we have 3 crests. Oh. Nope. My picture's bad. Hang on. Let's do this the right way. We have 3 crests underneath the dock. That one doesn't, I don't think this one counts because it's not completely under. All right, so let's try this again. Do you know what I'm gonna do? I'm gonna be smarter than this. Let's draw our wave first. Doesn't that make sense? All right, so we're gonna start with the trough. 1 crest, 2 crests, 3 crests, and then we're out from under the dock. So our dock goes from here, which is trough, to here, which is a crest. So this is our dock. All right, and the dock is 4 meters long. All right. So now we want to know what's the speed of the waves. So speed is defined as the frequency times the wavelength, isn't it? So we've got to find the wavelength and we've got to find the frequency. So how can we find the frequency? Frequency is going to be, we're going to have to look at this. Frequency is going to be defined as what? Here it is. Sorry, it was up here. Frequency is 1 over the period, and the period is the length of a wave divided by the speed of a wave, right? But it's also how fast cycles per second is frequency, okay? So cycles per second. So how many cycles did we undergo? What does this say? 25 crests pass by the first edge in a minute. Every time a crest passes through, isn't that a cycle? So we have 25 crests in how long?
60 seconds.
Mm-hmm. So we get, what, 0.42 hertz? Right? Okay, so now we have a frequency. Now we've got to find the wavelength. Think about what the wavelength is. Wavelength is going to be how long is, wavelength goes from crest to crest, doesn't it? So from crest to crest. So we have 1, 2, 3 of those, don't we? And then another what? Half? Does that make sense?
Because of the trough.
Yeah, because it starts at a trough and ends at a crest, doesn't it? So we've got 3 full crests and then another half. So this is 3.5 wavelengths in how many meters? All right, 4 meters. So 1 wavelength is how many meters? If we divide 4 by 3.5. So now we've got our wavelength. Picture becomes really important in these for being able to count them. So now we can actually find the speed. Now we can plug in 0.42 times 1.14 leaves me with a velocity of what? Okay, so 0.48 meters per second. It's not so bad, is it? Okay. So now, everything we've looked at so far is wave speed remains constant when it doesn't change medium. So what happens if it starts to change mediums? What do we know? Speed and wavelength change proportionally. Think about it. Doesn't that make sense? I mean, if you're going from one media in which it's going a certain speed and has a certain wavelength, and then you change to another medium that has a different speed and a different wavelength, within that medium, though, it's not going to change, is it? So it's proportionally going to change, and then it will be the same. So now what do we know? To change proportionally is wave direction, waves travel from one medium to another with different properties, but what remains constant? Frequency is going to be your guide to go between one to the other, okay? When the wave enters a new medium, three things can happen. You get reflection, transmission, or absorption. I want you to think about why that would be. It's either so hard that it doesn't absorb any of the energy and it just reflects it back off. So what's going to happen to the wave? It's going to go down to the new medium. It's not going to keep going through. Instead, it's going to come backwards and propagate back down the original path it was on. Make sense? Or you can have something that is even easier, that vibrates even more easily, that it moves, transmits more easily, and that means that it transmits it even better. So you take something that is doing a little bit of a wave and all of a sudden it becomes a bigger wave, doesn't it? Or you can go the other way around. It can still vibrate some, but it's not going to vibrate as easily. It's denser, so it goes from being like this to being like this. So you can go one of three ways. Reflect, it makes it better, makes it buries some off of it, all right? Wave reflection, a return of the wave from the barrier. Wave bounces off. We know that can happen. Now, here's the thing. Total reflection doesn't usually happen, okay? Some of it usually comes back. Some of it usually goes forward. Very rarely.
Unknown caller.
Not even necessarily splitting in half. Sometimes it can split in half, but sometimes it depends on how hard the new substance is, how easily or how poorly it transmits. So if it's a really, really, really hard substance, like you've got water going up to a hard glass plate, most of the wave, think about a wave machine, in an aquarium, most of the waves will reflect backwards. A little bit of it will vibrate the glass a little bit. If it was concrete, even less. It's just so more of it's reflected backwards, but a little bit will. Whereas if you were, say, an earthquake going through different layers of the soil, it's going to propagate. If it's going from, I want you to think about this, if it's going from hard granite to sandy soil, all of a sudden it's going to transmit much more easily, isn't it? And so a lot more of it will go through the sandy soil, whereas a little bit of it might not and might go back, okay? That's kind of what the idea is here, all right? So if the difference in wave speed between the two media is very large, so if the wave speed difference, if the difference is large, very little energy is transmitted and most is reflected back. Think about that. Doesn't that make sense? If you start by going really fast and then all of a sudden it's going really slow, that means not much energy was transmitted. Or if it's going really slow and all of a sudden it's going really fast, okay? The amplitude of the reflected wave and the transmitted wave are both less than the amplitude of the original. The original wave, by the way, is called the incident wave. It's the incidental wave. So what's coming in is, or what's going out is incidental, what's coming back is reflective, all right? So, at a free boundary, waves are reflected. At a fixed boundary, waves are reflected and inverted. What does that mean if it's inverted? Yeah. That's exactly it. So if it is a free boundary, in other words, if the end can move, that's what we mean by free. If you've got a big long string and you vibrate it, if the end is fixed, so it can't move, then it goes down. If it comes this way, then it comes back going the other way. So it does it, and you can see that if you reflect, if we were to tie a string off and reflect it, and actually we could do something with this guy right here. We'll take him out of his spring sock. I can do another spring sock. If we were to fix one end of this and start vibrating it, okay, both ends are fixed. What? I was like, why is this not coming undone? Why is it not coming? All right. All right, so now we've got this lovely spring coming out of this little thing. All right, so let's close this. If you pull that in, just hold the little end piece of it here. So you're gonna be the fixed end, all right? So now we're gonna do this, and you can actually, let's get it where you can see. You can see what's happening at the end very easily, can't you? Look at your end. It comes in, down, and goes out, up, okay? Now, that is your fixed end. Now if the end's not fixed. Too hard to see that way. Let's see if I can do it slowly. Do you see that it can move? Do you see what happens to the end? The end whips around, doesn't it? So it still comes back the same direction as it left. It's weird that way. So the only time you ever get that reflective back in the opposite direction is when the end is fixed. Otherwise, the end is free to continue to move with the wave and then move back. All right? So, kind of fun. But this is one of these really cool things where you can actually just see it. So, all right, so find a resulting wave for a pulse in a rope is shown below for the following if the rope is tied to a pole. So if the rope is tied to a pole, does that mean does that count as a fixed? It doesn't, does it? It can still move up and down, can't it? Think about it that way. All right, so if it is going this way, can you tell that it's moving that way? How? Because the crest is moving that way, isn't it? So then what's going to happen to it traveling back? It's going to go the other way, but is it going to be inverted? No. All right, so if we were to draw this, we would simply draw it as going back this way, wouldn't we? So now it's going that way. Okay? Now, what about if it's attached or fixed to a pole? That's considered a fixed end, isn't it? So is it going to invert this time? It is, isn't it? So it's still going to be showing that it's moving the other direction, but it is going to flip over. Okay? Feel confident with that one? All right, so refraction. Remember I said we were going to be getting into light as well. Light is a wave. So what happens when we go from one medium to another? And we'll get back into this when we get into optics in just a couple of days or next week. when we change medium, in other words, say we're going from glass to plastic, you can't always see straight through, can you? What ends up happening? It ends up looking what? Distorted. That's because it's changing media. The light is changing media before it gets to your eye, and you're seeing that change and it comes out as a distortion. That's because the wavelength changed from one media to another. As the light went through the glass, it went at one particular speed, and then as it hit the plastic, it changed. And so what ends up happening, what you see is what you see here. It's going to either be going one angle and then it's going to all of a sudden be going more shallow, or it's going to be going and it's suddenly going to come out and it's going to be more steep. Does that make more sense to you? All right, so how do we know what's going to happen? We know that the direction will change. Look at the picture. Okay, if the direction changes, and think about what wave speed is. Wave speed is frequency times wavelength, isn't it? Well, we just said what? The frequency doesn't change. So if the wave speed changes, then what has to change? If this doesn't change, this stays the same. Yeah. So as V changes, the wavelength has to change. So the direction is going to change and the wavelength is going to change. Okay? And since that's what you're going to see with this angle changing right here. If we're going from air into a medium, air is not that dense, is it? What is dense is going to be the medium. Think of a beam of light going through the air and then going and hitting a piece of glass. It's going to change wavelength. In other words, it's going to look like it's bending because it's changing wavelength. It's changing wavelength because it's also changing speed, if you think about it that way, right? It's getting more dense. So as it gets more dense, it's going to slow down. If it slows down, then the wavelength changes and we see it bend, okay? If it's going from a medium into the air, of course, it's going to speed up because it's less dense. So it speeds up, so it refracts more than it does in the other direction. It kind of makes sense when you think about it. So it's doing what it's supposed to be doing. So we've got a wavelength of 4 meters and a speed of 5 meters per second, enters the new medium. In the new medium, the speed is 7.5 meters per second. So if the speed went up, what do you know about the wavelength? It also has to what? Go up. But it's going to be proportional, isn't it? We know that the frequency of the first is going to be the same as the frequency of the second, isn't it? That is what we know. Well, think about what frequency is. Frequency is velocity divided by wavelength, isn't it? Look at this. If we solve this for F, it's velocity divided by wavelength. So it's the velocity of the first one divided by the wavelength of the first one is the velocity of the second divided by the wavelength of the second, isn't it? And then what we have to do is fill in. So what is the wavelength of the first one? All right, so we've got 5 divided by 4, excuse me. It's velocity divided by its wavelength. So 5 over 4. New speed is 7.5 over the other wavelength. And then we can just cross multiply and divide, can't we? 4 times 7.5 divided by 5. What do we get as our new wavelength? Mm-hmm. 6 meters. All right. So that is refraction. Now we're going to talk about diffraction. We've got refraction and diffraction. Refraction is bending. Diffraction is sort of like diffusion. Think about it with light. When we diffuse something, it gets more spread out, it gets weaker, more watered down, doesn't it? Same thing with light. Diffraction is where it spreads out. Typically, diffraction happens when you have an opening or a slit. If you've ever looked, and when we look at optics, we're going to look at slit experiments where you have light going through a slit. And if you've ever looked, what happens if you've got, like, in the morning or something, you've got your blinds open, but they're just barely opened? You get cool patterns on the walls and the ceilings, don't you? That's from the diffraction of the light. Every place where it hits a slit, it spreads. Okay? So if you've got a bunch of those happening and you've got all of these spreading, think about dropping more than one pebble in the water of a pond. The first one ripples out like this, doesn't it? That's those diffraction waves in the water. If you put a second one in, you get another diffraction wave going somewhere else. And where the waves meet, sometimes the wave gets bigger, sometimes the wave kills itself out, sometimes it's somewhere in between. That is interference, which we'll talk about next. But diffraction is that case of something happening, like you have a slit with sound or something along those lines, where you are either making it amplified or spreading it out or making it smaller. So spreading of a wave out behind an opening or an obstacle. And it doesn't just have to be an opening. It could be like a rock in a stream. If we've got a stream that's got waves coming at it and we've got a rock sitting in the middle of it, what's going to happen is it's going to spread it around that rock, isn't it? That's that same idea of what's happening with this diffraction. So it can either be a slit, think of it this way, a lot of blockage with a small opening, or a big opening with a small block. Either case is like, okay, so we're either going to leave the block in or we're going to take it out. But it's still an opening, all right? So that is what we call a diffraction. Now, practicality. When do we we're talking sound here and light. We've already talked about light a little bit. We've talked about energy like in water. Can you think about a case where we actually use diffraction with sound? Go stand outside my doorway while I talk. If I talk in here, do you hear it out there? Do you hear it as well? No, it's not as loud because it's more spread out, isn't it? So since we've increased the wavelength, then what ends up happening is the amplitude decreases a little bit, which is your sound. Okay? So you lose some energy, basically, as it gets further away. It loses some energy as it goes out the door. It's also the reason why you can hear around a corner. Think about it. The corner is sort of like it's sort of like a block. Okay? So you can hear around corners. You can hear outside doorways. You can hear in a closet. If you're sitting in a closet, you can hear what's going on. Sometimes things like that. All right. So interference. When two waves traveling through the same medium meet. And we talked about this. So you drop one pebble in, you drop a second pebble in the water. What happens? You get certain types of interference. So before interference, you've got one wave coming this way, and you've got another wave traveling the other way. What happens when they meet? Well, during interference, they're going to sort of cancel each other out, aren't they? Think about why that is. Think about during interference why we get nothing. Immediately, as they're meeting each other, you've got one that's going up and the other that's going down, aren't you? So what's going to happen with those? Everything up top is going to cancel with everything out. Okay? So they're going to kill each other out at the just exact, now, only at that particular moment in time. Every other time you'll have some up, some down, and it'll go. Okay? So now, after interference, they just keep on going. This guy is now going to be down here going this direction, and this guy is now going to be up here continue to go in that direction, isn't it? They pass by. But as they are interfering with each other, they're canceling each other out. That's what makes it destructive. All right? Notice for destructive, a trough and a crest have to be lined up exactly opposite each other at any given time. Now, that's destructive. Constructive interference is like, have you ever been in a concert, or have you ever heard something when all of a sudden somebody gets on, or like you're on a Zoom call and you're in the same room? What happens? Yeah, it goes up in noise too, doesn't it? And sometimes you get like speakers will catch something and they'll all of a sudden go way up. That's constructive interference. Okay? What that means is this. Before interference, you've got them both up instead of up and down. Like they're not opposites, they're the same. So what happens during interference when they meet, you got wave 1 and wave 2, and all of a sudden you've got a peak here of both of them, don't you? And that's what causes those things where, that's why it sounds like it's pulsing, number one, when you're in a Zoom call with two people with phones on in the same room. That's why it doesn't just all of a sudden go really loud. It kind of goes off and on and off and on and off and on. It sounds like it's cycling almost. That's those waves constructively interfering with each other at the same time. They don't do it constantly, but they do it at certain times. Now, after interference, they're both still going to keep traveling. And you've got one traveling this way and the other one's traveling this way. But during interference, it's building instead of canceling out. So constructive builds, right? All right. So what is a traveling wave? What is a standing wave? We need to talk about what a standing wave is. Standing wave means that we are fixed at both ends, okay? If both ends of our spring are fixed and we begin to vibrate it, what happens? It's going to be reflected back how? What did we say happens? If we've got a fixed, if we're vibrating that spring, it's inverted. But now it's fixed at both ends, so both ends, it's going to continue to reflect on itself, isn't it? But both ends are going to be inverted, aren't they? So if we've got something that looks like this, that's our original wave. What is our reflected wave going to look like? Exactly opposite, isn't it? Okay. It's going to be exactly opposite the other. All right. So now, these places where it meets, these are what we call nodes. And the places where they're opposites of each other, these are called antinodes. Now, nodes are location of destructive interference. I want you to think about why those would be destructive interference. What's happening here? It's at 0, isn't it? Where they meet, they're at 0. Antinodes are locations of constructive interference. All right? So now, what does that mean? Standing waves on a vibrating string. How much experience do you have with music? That's okay. I just want you to understand what's happening here is when we talk about harmonies, those are certain sounds that go together really well, aren't they? And first harmonic, second harmonic, third harmonics, etc., that really is a physics term. And what we've got, if we've got a first harmonic, is we've got one node, antinode being created between two nodes. So it's just reflecting back on itself. That's first harmonic. Second harmonic means we, instead of having one of these, we have two of them, okay? Third harmonic would be 3. Fourth harmonic would be 4, okay? So a harmonic number is equal to the number of antinodes. In other words, you can just count them. 1, 2, 3. 1, 2, 1. Make sense? Now, only certain frequencies create standing waves. Not every frequency creates a standing wave. All right. If it does, then the fundamental frequency of the first harmonic is your lowest possible frequency, resonant frequency. It's the lowest possible is your first harmonic. So first harmonic is your lowest possible. And they are integer multiples of fundamental frequencies. just for the fun of it, let's see if we can do this. Hang on. So your first harmonic is 400 hertz. Your second harmonic is at 800, third harmonic is at 1200, fourth harmonic is at 1600. Okay. Makes sense? Kinda? Kinda, sorta? All right.
Oh, is this like those things, I seen them on TikTok where they like the sound gets like, it'll do like a ringing and it'll be like this is the first harmonic and like most people can hear it, and as it gets like louder, less people can hear it.
Sometimes, yeah. All right. I can get this up. Can I?
Back in the video band for Unit 9, I learnt something about the maths of rhythm and the beat in music with this band, Betty's Kitchen. Well, today I'm hoping to find out why each musical instrument has its own characteristic sound. What exactly is going on that distinguishes a guitar from a fiddle? I'm presuming it has something to do with this jazzy little display here that lights up as the music plays and claims to be telling me something to do with the frequencies. Well, to be honest, I've always wondered.
So those frequencies are the harmonics.
I guess it has something to
So
do with
each
how loud the notes
instrument
are,
has its
from
own
low and high. But I'm hoping
harmonics.
that Alan Graham, who I teamed up with last time, is going to make it all crystal clear. Right, I'm just going to give Alan a call on the mobile phone. Hello, Alan. It's Janice.
Hello, Janice.
Hi. I want to come around and talk to you about music again.
That's fine. We've got a gig tonight, but maybe you can join us at the rehearsal this afternoon.
Great. All right. I'll see you later then.
Yep, see ya. Bye.
Okay. Bye.
I'm just going to take it out of touch.
I played it all wrong anyway.
Okay, let's try it from the beginning of part 2. 2, 3, 4. Hello, Janice.
Hi there. How are you? Nice to see you.
Anyway, we're just about to have a break, so shall we just stop for a while?
Yes. Great. That sounded great, then. Well, I've come for my music lesson and to hear the performance later. But can I start with basics? When you're all playing the same note on your instruments, each note sounds different. Why is that?
Well, to understand that, I think you need to know how a note is made up. Let's take a very simple example of a tuning fork. When the tuning fork is struck, it gives a pure, simple note, a single frequency. And let's look at the trace that it produces. Because it's such a pure note, it gives a perfect sine curve. When a tuning fork is tapped, The prongs, or tines, have been designed to oscillate at a particular rate. Look at the behaviour of just one of the prongs. It starts at rest with zero displacement from the horizontal. Plotting the displacement against time gives you a regular sine curve. One peak and one trough together represent a single cycle of the sine curve. A fork that's tuned to middle C will produce a cycle 256 times a second. This frequency is often described as 256 Hertz. So you've got this graph by plotting amplitude, that's the vertical displacement from the horizontal, against time.
So does it matter how hard you hit the tuning fork?
Well, you might be tempted to think that if you strike it harder, the tines or the prongs vibrate more quickly. Well, that can't be true. This is a tuning fork in C. It will always strike C however hard you hit it. But if you strike it harder, and let's see what happens. And that's what it looks like when I hit it hard. You can see the amplitude has increased.
So the peaks and the troughs are more extreme, aren't they?
That's right. So strike it harder and it gets louder, but the pitch doesn't change.
So the amplitude tells you how loud the note is.
That's right, yeah. Tap the fork harder and the prong is displaced by a greater amount. You don't get a greater number of oscillations per second. What you do get are oscillations of a greater amplitude than before.
So if you think about
Each of
it,
these-
that's why the frequency doesn't change. The frequency is how many of those cycles you're getting per second. And that's not going to change based on the type of media it is. That's why we say the frequency doesn't change. But the amplitude, how fast or how fast it vibrates doesn't change, but how extremely it vibrates does change.
Can I run to the bathroom?
Sure. a minute.
So there.
That's what it is. They're both gone on golf. It happens. All right. So let's keep going here and finish up. Almost there.
Curves has the same frequency. That's one cycle every 256th of a second. It's only their amplitudes that differ.
So Alan, if you change the note you play, how does that affect the trace you get?
Well, you've seen the trace for the note C. Now this blue tuning fork is tuned to A, that's the A below C, so it's a lower note. And if I hit that one, I'll just have it trace. This lower trace is the one for A. And the waves are more widely spaced out here than they were with the higher note. The reason being that with A, the frequencies are less, so that they're more widely spaced. But there's no real difference in the amplitudes because I struck them both quite gently.
So in fact, the compactness of the waves tells us whether the note is higher or lower in pitch.
That's right, yeah. This fork is tuned to the note A below middle C. As such, it's been designed to oscillate at a frequency of 220 Hz. This new note in blue vibrates more slowly, so its peaks and troughs are slightly more spread out, with one oscillation every 220th of a second.
But Alan, here you're talking about pure notes. What do these traces look like for real instruments?
Well, let's hear a real instrument. Maura, if you could play us two notes. First of all, play us a soft A.
Okay.
And that's the trace. Now, a loud A.
Well, they're a lot messier, aren't they?
They are a lot messier, but there are some common themes. First of all, there's a regular repeating pattern. But secondly, the soft note had a much smaller amplitude than the loud note.
So what's all this messiness about?
Well, on a real instrument, when you play a note, it's not just the note that you play. That sets off a lot of other notes called harmonics. So what you're hearing is the fundamental note that you have played, combined with the various harmonics that have been set off.
And how can you tell what these different frequencies are?
Well, it turns out that the frequencies of the harmonics are exact multiples of the frequency of the fundamental note. Here's a demonstration. It's like a big version of a fiddle string. There's a motor at one end which jigs up and down to set the string vibrating. At a certain frequency, the string forms a steady wave. This occurs at the fundamental or first harmonic frequency of the string. Doubling the frequency of the motor gives you the second harmonic. At 3 times the fundamental frequency, you get the third harmonic. And so on.
So I can see there are different harmonics, but how do you know how much of each harmonic there'll be for a particular instrument?
Well, it's pretty hard to separate them out from the sort of graph we've been looking at. It's very messy. But there's another way of representing that information. You can separate out each of the harmonics and represent each one individually on a different type of graph called a frequency spectrum. But with a frequency spectrum, instead of having amplitude against time, you have amplitude against frequency. Here's the waveform graph for the pure note C at 256 Hz, with amplitude plotted against time. You can represent the amplitude of this note in a different way on what's called a frequency spectrum graph, by plotting amplitude against frequency. A frequency of 256 Hz can be represented as a point on the horizontal axis. The height of this spike on the graph then represents the amplitude of the note of that frequency. Now, here's the waveform graph for the note A. It shows two differences from the previous note. The pitch of this note is lower than the last one, so the frequency of 220 Hz is at a point on the horizontal axis that's slightly closer to the origin. This new note also happens to be quieter than the previous note, and so, in this case, the amplitude at 220 Hz appears as a shorter spike on the graph than the spike at 256 Hz. So this is the waveform for the fiddle, and this is the corresponding frequency spectrum. And you can see this is the spike corresponding to the fundamental note, and all of these are the various harmonics.
And you can tell how much of each you need by looking at the amplitude there.
That's exactly right, yes. And you could do that for any instrument, but this is the characteristic shape of the fiddle. If you like, this is like a fingerprint of what a violin sounds like.
So I've always wanted to play the saxophone, and so you've got one there. So breaking it down like that, I could go away and make my own saxophone sound.
Yes, why would I play you a note? Take it away, and that's the fingerprint of your own saxophone.
And this is how they do with sound blending, like electronically sound blending. If you think about it, that's how we're. So that's why digital sound has become so much better, because now they can actually go through, find all the different notes that all the different instruments are playing, and they can literally digitally pull them out or add additional in. They can blend and make songs just from straight up digital signatures, because they know what they are for each of the instruments layered together. It's pretty cool. Sound engineers have to know wave physics. All right, so let's look at an example. Or are we about to leave? What time are we out of here?
30.
How many?
30.
3 minutes? Okay. I think we'll stop here. We're almost done. This was our last example problem. We'll pick up here last time. You should still be able to do your homework problems. And you should try this one and see what you think. Okay? Based on the formulas you know. The big formula being velocity equals wavelength times frequency, right? Yeah, we had